So today we're going to take a look at the first half of section 5.1. We're going to talk specifically about addition and subtraction of integers, and I think addition is as far as we'll get today. Before we can actually talk about addition and subtraction of integers, we need to talk about what they are. So our integers look like the numbers from negative infinity to infinity. You can talk about them being the whole numbers, no fractions, no decimals. They're positives and they're negatives. Your book uses an I when it talks about these numbers. That's why this says I equals. But you need to be aware that that's not typical notation. Most books use the letter Z, and they put that double line through the middle of the Z. There's a couple of reasons for that. First of all, Z is used because it's the Latin letter that starts, or Latin sound, I guess, maybe that starts the word for integers in Latin. Secondly is because the I is often used for irrational, and so because we have two different I words, they can't both be I, and so this is kind of the default as is not using I for integers. All right, so what I want to show you is I want to show you 4 different methods that can be used to explain why we do what we do when we add integers, okay? So in the examples I'm going to use, they're all exactly alike. They're all 5 plus negative 3. So the first method is called the chip model. These can actually be done, tactile learning people, with like poker chip kind of style pieces. Obviously, I'm going to draw them on the screen for you. But if you were doing this in the classroom, they actually sell math manipulatives that are poker chips. But they're kind of cool. Most of them that they sell are usually one color on one side and one color on the other side. So these chips are usually colored red on one side and black on the other side. It doesn't have to be that way, but that's usually the way that it works. So if you happen to have another color with you, if it's red, more power to you. That'd be fabulous. But if you have 2 colors, if you'll get out a couple of colors right now, that'd be amazing. If you don't, you can fill them in solid and empty as we're drawing the pictures, okay? So it's okay if you don't, but the image will kind of be a little bit clearer maybe if you did. So to start with, I'm just going to draw a circle. And let me get my different objects. So that's going to be, make it a little bit thicker. This is going to be my red chip. And this is going to be my black chip. So here's the deal. A red chip represents a negative value, and a black chip represents a positive value. Now, if you don't have red and black and you're using pink and purple, or you're using open circle, closed circle kind of images, you just need to write down that that's the key. Like that's what you're choosing. So maybe your pink is your negative chips and your green is your positive chips. It doesn't really matter as long as you know which is which and you write down for me which is which, okay? So feel free to use other colors. The idea behind this is that all of the positive, or all of the numbers that we're given over here, are represented in our circle image in this set with chips that correspond to them. For example, this is the number that's positive 5, so what would you guess I would have in my circle? 5 black chips. Now, black and red are usually the colors that are used because in finances, your spreadsheets do this and other things too, a positive number is usually considered in the red, right? I said that backwards. A negative number is considered in the red. It means you owe money, it's a debt. And a positive number is considered in the black. It means that you actually have a positive or an above 0 count. Speaking along that way, do you know why Black Friday is actually called Black Friday? It's because for many businesses, the entire year up to Black Friday, the companies are in the red. And not until Black Friday do they actually start making a profit for the whole year as a whole. Crazy, right? Crazy stuff, but that's actually where it got its name originally. Obviously, that's not an every company kind of thing, but that's where it originally got its name. All right, so what else do I need in my circle? 3 reds, you got it. Now, there are pieces that are in my circle that if I put them together, they're called a zero pair. If you've taken proportional statistical reasoning, we talk about this with algebra tiles, for those of you who've had that class. If you've not had it, then you get something to look forward to. We're going to talk about this idea again. So a positive and a negative put together make a zero pair. It just means that when they're combined, they zero each other out. Okay? So we can pair these up and remove them in pairs because they zero each other out. And when I do that, what am I left with in my circle? 2 black dots. So this is the number 2. So this is one visual. This is one that's really good for tactile learners. Think about what you would do. You would actually physically take the 2 chips and remove them from the circle until there's nothing left and your image at the end looks like my final circle. Okay? The second picture that I'm going to show you is almost identical to this. You don't need colors for this one though. This is called a charged field model. Did you ladies have a question? I'm sorry.
Oh no, I just said I wish I would have done this when I was younger. I don't think I did it like this.
Yeah. And I'm going to show you 4 methods. So you're saying this one makes sense to you, and there may be someone else in here that's going, this is stupid, why did she just show me this? And that's okay. Not all your kids are going to think the same way. So I always think it's a really good idea to have multiple ways to express something. So when that kid looks at you and their eyes are glazed over, you have a second, a backup response to be able to give them. So this one almost feels just like it, but it does it with positive and negative charges. So what we're going to do is that when we have a positive number, we're going to write down a plus sign for it, and we have a negative number, we're going to write down a negative sign for it. So for lack of clarity, I'll go ahead and write this down just in case. So the idea is that you have you have a 5, and that's a positive, so you write down 5 pluses. And you have a 3 that's negative, so you write down 3 negatives. And then again, 0 pairs cancel each other out. Their charges cancel. So children that have done a lot with, think about like batteries, the positives and negatives on batteries and things like that. Some of these symbols might make more sense to them than maybe the red and the black chips. Like that just doesn't connect for some reason. So we can pair up positives and negatives, again, because they're 0 pairs, and we can remove them. And of course, the end result would have been the same thing. I would have 2 positives for the number 2 inside my circle. This is not very tactile learner, right? I mean, like, I don't have, as far as I know, there aren't any manipulatives that are actually pluses and minuses that I'm going to throw in the circle here. But they have more to do with the signs that we use in front of the numbers themselves. The third model is the only one that I ever remember being shown as a child. And so it's called the number line model. I'm going to show you a couple of versions of the number line model. I'm going to show you one on the screen, and then I'm going to actually act one out. So you've got your kinesthetic learners. We can talk about them too in this particular one. So on the number line model, we're going to mark out our 0. And then because it comes first, that's the only reason I'm going to do the first one 5. So moving 5 means moving right 5. So now I'm at 5, so to speak. I've kind of jumped over here 5, jump them one at a time. I don't care how you draw the arrow, but you have now moved 5. And this one right here tells me that I need to then move 3 backwards. So if you want to count them again one at a time, you could. You can go 1, 2, 3, or you can make all 3 of the jumps at the same time. Wherever I landed right here is my answer then, and of course that answer would be 2. I know this is the only model I ever saw when I learned this, and maybe it is for many of you as well. Now, if you think in terms of a number line being actually on the floor, and you could do this pretty easy with minimal cost. I mean, get some tape and you can mark it out. I can do it in this classroom because the desks are very nicely spaced in rows. So if this is my 0 row, where this is my daughter, by the way. Say hi, Abby. If this is my 0 row, we can actually count forward 5 desks, right? So we can go 1, 2, 3, 4, 5, right? And then we can go backwards 3. We can go our 1, 2, 3. And the question is how far from where I've started? And the answer is 2 desks. I would have to go 2 more to get to where I actually began. So you could actually do this physically moving around as well. It's a number line model. The last model, most people are not fans of this model, so I'm going to just go with that for right now. But there are children, if you think about some of the different kids that you might deal with special needs, where patterns are how you think. Autism is the one that's kind of coming to my mind, Asperger's, those kind of on that spectrum, that patterns are really important to some kids. And so if we establish the result based on a pattern we already know, that can be really useful for those types of children. So what we do is we start with numbers that we already know how to add from previous work, and that would mean they'd need to be positive numbers. I don't want to get too far away from the -3, so I'm going to start with the number 2. There's nothing magic about me saying 5 plus 2. I just need to be able to establish the pattern before I continue and move into my negative numbers here in a minute. So I'm going to do 5 plus 2, and if I do that, what do I get? 7. And then I'm going to just decrease the 2 to 1. 5 plus 1 then would be 6, and 5 plus 0 would be 5. Now, that's all prior knowledge kind of stuff. But by doing so, what we've done is we've established a pattern. So what you notice is what happens as I go sort of down the right-hand column of this table almost that I'm creating, this list. It decreases by 1. And so the reason that matters is because then I can continue the pattern by taking the numbers, again, that are coming after the 5 plus and decreasing them. So now I've got -1. So the pattern on the right would then tell me this has to be 4. And then I have -2. Again, the pattern on the right then tells me this has to be 3. And then I'd have -1, and the pattern on the right tells me then I would end up with, oops, I didn't mean 1. I meant 3 there. My bad. -3. The pattern on the right then tells me I would end up at 2. Okay? So it's establishing a pattern based on something that you've already learned. We're going to take sort of a little deviation before we get into the subtraction part. We'll do the subtraction part next time. And we're going to talk about one other component in this section, which is absolute values. Okay, so to start with, by definition, an absolute value, if the value of x is bigger than 0 or equal to 0, then the absolute value of x is x. I had some students working, and I'll just simplify the portion of the problem they were working on. They were working on it in my business calculus class. And I literally had somebody ask me the other day if they were putting this inside of something else in their calculator, if they had to put the absolute value signs, and I said no. Because what's the absolute value of 7? It's 7. So there's no reason for them to actually include the absolute value signs in that particular argument, right? If the number's already positive, we don't need the absolute value signs, okay? Now, if the number is negative, what we do is we remove the absolute value signs and we change the sign. Now, you probably think of it more like I remove the negative, right? I get rid of, let me change this. I get rid of this piece. It goes away with the absolute value signs, okay? However, like notationally for mathematics, the way that we represent changing a sign is that we put another negative on it. So notice what happens here in terms of like numerical values. If I have a negative number inside, what I am saying is I remove the absolute value signs, and then I take the opposite of the number that's inside. So what happens to those two negatives? Yeah, they cancel. It's just a notational issue because we don't have another notation that says, and remove the negative. So if you put an additional negative on, it will cancel the negative you already have, and that has the same effect. Okay? Now, in terms of actually what absolute values do, absolute values actually measure distance. It's all about distance. So if I have the number 0 here, and I have a 7 here, and I have a -7 here, what I'm saying is that the distance between 7 and -7 back to 0 is the same. And that's how we talk when we talk about distances as well, right? If I ask you, how far is it from your home to Shawnee, where you live in the dorms? You're going to have a number. And if I ask you, well, how far is it from your dorm back to your home? It's going to be the same number. And in neither case would you tell me a negative, right? But we do recognize, of course, the direction you're going would be the opposite direction, but the number is still a positive number. So what we're going to do is we're going to classify some statements based on these arguments. So, well, we're just going to start before I talk too much and give things away. We'll see how we go. Classify as true or false, and if it's false, show a counterexample. Remember, counterexample means an example showing that it really doesn't work. So, absolute value of x to the fourth is x to the fourth. What do you think? True or false? It's true. Now, it doesn't say to justify why, but we probably should, so we make sure we have a clear idea of how this one maybe is different from any others that we do. Why is this a true statement? Emily?
Is it like because if you have a regular Sunday lunch, it's already
Okay, it's already positive. The x to the fourth is already positive. Is that what you're going to say too, Taryn? In even power, which makes it positive. Exactly. So no matter what x is, positive or negative, if you raise it to the power 4, because 4 is even, you're going to end up with a positive number. So you can try it. Really, the concern is to try it with a negative, a 0, and a positive. So obviously, if I try it with a positive times a positive times a positive, however many times is positive, right? So I can remove absolute values if it's positive. Nothing wrong with that. What's 0 to the fourth? 0. Don't overthink it. It's 0. Yeah. And what's the absolute value of 0? 0. So we can remove those absolute values, no problem. And then we try a negative. Let's try negative 2. What is negative 2 to the fourth?
16.
It's 16. So let me write that one down. If I had negative 2 to the fourth, that would be negative 2 times negative 2 4 times. So what happens when I multiply 4 negatives together? I get a positive. So this item over here is always positive. So x to the fourth is always positive. And I'm even going to write down what Taryn said because I think that's a valuable piece of information. It's because for the power, I'll say it that way, because the power or the exponent is even. So, what about part B? It's false. Erica, you seemed pretty quickly to tell me that. Can you give me a counterexample?
If you did negative 2 to the fifth, then it'll be negative 32.
Yeah, negative 2 to the fifth is negative 32. But of course, if you absolute value that, so to speak, you would get a positive 32, right? Why? Why did the last one work and this one didn't? The exponent in last one was even and the exponent here is odd. That's why that's happening. Okay, C and D. Very similar. C says the absolute value of x is not negative. Okay, remember, this absolute values are distances, so we could replace the absolute value of x with the word distance. Distance is not negative. True. That's a true statement. So what about D then?
True. No, it's not positive work.
Okay. The answer is false. But if I put false, it means I need to create a counterexample. Is there any number that could be a distance that's not positive? Say it louder.
0.
0. It's a nuance you have to be careful of. There are 3 types of numbers when it comes to integers. There's positive, there's negative, and there's 0. 0 is not negative, which is why this statement on C is actually true, right? 0 is not negative. A distance could be 0, so that one's okay. But 0 is also not positive. So we can't say that all distances are positive. Now, could we say that most of them are? Well, we could. But at least we can't say that all of them are. Okay? All right. One last piece of information we're going to go through today are our properties of integers. You have seen almost all these properties before when we did properties of whole numbers. So I'm going to let you help me, as you remember, with telling me what these properties say. Closure is the one that people kind of get a little skittish on. So I'll do that one, and then I'll let you guys help me with the next couple of them after that. Closure property of addition. The closure property says that if you take integers, we'll take two of them here, it says a and b, that a plus b is a unique integer. You add two integers together, you get another integer. It doesn't become a fraction, it doesn't become a decimal, it doesn't turn into a pi. Nothing like that can happen when you're adding integers together, you just get other integers. All right, somebody tell me what the commutative property says. Right, with addition, a plus b is equal to b plus a, because we're working with addition here, you bet. Order doesn't matter, right? The order of addition doesn't make any difference. What about the associative property? You got to have 3, that's right. Yeah, the A still comes first, so we don't change the order. But now the parentheses are around the B plus C. So remember, it's all about grouping. Who are you grouped with? Who are you associated with? That's the associative word in there. And in the first case, the association is with A and B. Here, the association was with B and C, but it doesn't make any difference. I actually get the same value either way. And the last one on this page, which is where we're going to stop for today, is the identity property of addition of integers. Now, maybe about a third of you are still working on the identity question on your test, where it talks about the addition and the subtraction and the multiplication and division and which one have identities and what they are and why. Do you guys remember that problem? I think it's problem number 5. That's what I'm remembering, okay? Do you remember what the identity element is for addition of whole numbers? It's 0. So the identity element, this is like bonus for those of you who are still working on this problem on the test. The identity element is 0. And the reason why is because if I add 0 on either side of a number, I get back the same number. Okay? Does that work for subtraction? No. What's wrong with subtraction? I mean, like a minus 0 is a. 0 minus a wouldn't work. So because the order is not commutative with subtraction, the identity won't commute either, which means it's not actually an identity. All right, we'll pick up here next time.